Okay, let's revisit an earlier example where we saw the limit of this function as x approaches 2. And if we plug 2 into this function, we said how we're going to get 0 over 0. Now we actually have a name for this. This is called indeterminate form. So we found the answer last time using a table. Our technique this time is going to be to find our limit algebraically, but this time using a factoring method. So direct substitution yields 0 over 0. However, notice that if we were to factor this, this is x plus 2, x minus 2. These x minus 2's are going to cancel. So if I rewrite what's left here, we have the limit as x approaches 2, and we're left with the quantity x plus 2. Well, from there, I can apply my direct substitution, and recall we got an answer of 4 when we looked at a table of values. Okay, so the factoring method is simply you're going to factor, you're going to cancel out your common factors, and then you're going to resubstitute. Now, those common factors create what we call a whole. So let's jot that down. So this is a really important point. So jot down that common factors create wholes. So we have a common factor of x minus 2. If you take that common factor of x minus 2, and if you were to set it equal to 0 and solve, you get x equals 2. So we say that we have a whole at 2, 4. So recall that when we graphed this earlier in the other video, we said that the whole was at 2, 4. Okay, now that's the location of the whole. The limit is just 4. Remember, a limit is a y value. Okay. So sometimes in these limit problems, you're going to have advanced factoring that is required. So it's possible to see the sum or the difference of 2 cubes. So let's first start with our sum formula of 2 cubes. So x cubed plus a cubed can be factored into x plus a, so that's a binomial. Notice the signs are both positive here if we compare this to that. And then we have a trinomial. Notice how the sign changes, it's the opposite. Okay, we have x squared minus ax plus an a squared. So let's apply this to an example. Let's suppose we have x cubed plus 8. Well, understand that our 8 is really 2 cubed. So if we were to factor this in our formula, the so-called a is 2. So we would have x plus 2 times, we'd have x squared minus 2x, and then 2 squared would give us our 4. Okay, now let's talk about the difference of 2 cubes. So here's our next formula for the difference of 2 cubes. Look how similar it is to the sum of 2 cubes. Notice the signs start off the same for the binomial piece, just like it did with the sum piece up above. And then this is virtually the same, except once again we see an opposite sign there. Notice the a squared term on the end is positive with each of these. Okay, so suppose we wish to factor x cubed minus 27. Keep in mind 27 is really 3 cubed, so the 3 is really the a in the formula. So we would have x minus 3 times x squared plus 3x plus 3 squared, which we'll write as 9. So let's look at one more example of a limit problem where one of these formulas will show up. Okay, in this problem we have x cubed minus 64 all over x squared minus 16, and x is approaching 4. Now don't forget, our first step always needs to be to plug in. So if I plug in my 4, apply my direct substitution there, we end up getting 0 over 0, so that indeterminate form. So you want to see if you can factor. And in this case, we certainly can. So we'll start in the bottom here, since this is the easier one. That's x plus 4, x minus 4. In our numerator, we have a difference of 2 cubes. Keep in mind that this 64 is really 4 cubed. So this can be factored into x minus 4 times x squared plus 4x plus that 4 squared, which is 16. Now from there, let's rewrite this. Carry along your limit notation as x approaches 4. Notice we have these x minus 4 factors that'll cancel out. We're left with x squared plus 4x plus 16 all over x plus 4. And finally, let's do our direct substitution. If we drop in a 4 everywhere, we get 16 plus 16 plus 16 all over 8. When we clean that up, we get a final answer of 6.